talking about a bow and arrow, although wind resistance really messes with bows and arrows.
Mr. Punjab.
We're talking about bullets. We're talking about a person shot out of a cannon. Right. Now, okay, parametric equations. Here's the deal. Okay, you guys have been doing a little bit of this, but I want to more explicitly tell you what you've been doing. All right? With a parametric equation, I'm going to give an oversimplified definition. I'm going to give you a definition that will work, but your college professors will probably tell you it's not quite true. Okay? Here's what it is. For our purposes, dimensions are visible. Parameters are not visible. Dimensions are visible. Parameters are not visible.
What about like the fifth dimension?
I know. Yeah, the fifth element is love. Yada yada yada.
What?
I know. There's a this particular part of the definition most modern physicists would say is not true, but I'm trying to get you through an early concept in math. So plan on this being contradicted. Okay, so dimensions, on the two-dimensional graphs we're doing, dimensions are the x and the y. Okay? The dimensions are x and y, vertical and horizontal change in location, and the parameter we're going to talk about for ballistic trajectory is time. So we're going to look at the horizontal and vertical position separately, and we're going to have each one described by time. Okay? Honors pre-calculus, you'll hear more about this later.
I know what it is now.
But like later today?
No, later in life, maybe December.
This isn't that bad.
No, this isn't that bad, and we're only doing one part of it. We're not going into all the circles and stuff you might remember from last year, Johnny. Okay, so dimensions are visible, parameters not visible. Parameters, for example, are when your graph is affected by things like time, temperature, pressure, things that aren't actually location related. Okay? Parameters, invisible, dimensions visible. That'll get us through this lesson. Again, prepare to be contradicted, particularly on this one, if you study a bit more physics.
We're not dealing with time?
We're dealing with time. We're not going to deal with like temperature and pressure right now. Okay, I need to erase this. You guys ready? Good with that?
Ready to go. Mm-hmm.
Okay. All right, so when you throw something, when something is thrown, shot out of a cannon, whatever, I'm going to use a vector to represent the initial, not velocity, I'm sorry, the initial, I'm not sure how to say this. The initial change in position of a thrown body. I don't mean body of like a person.
Yeah,
I mean
throwing bodies.
Body in the physics sense. Remember, a particle, all you care about is location. A body, all you care about is location and mass.
What is this? What does this mean?
Okay, initial change in position of a thrown body. Sarah, I throw something. And by something, I mean anything that just where I care about its position and how much it weighs, okay? All right. Well, hang on. Give me a minute to finish. All right.
Okay.
Short attention span, child.
Okay.
Stretch your attention span.
No.
All right.
The attention span of a squirrel, okay?
Look, Peanut. Okay. So.
Actually made me look good.
I know. Okay. When you throw something, okay, it has an initial velocity. And if you want to know how far it's going to go, you multiply that initial velocity times time.
Is that meters per second times time?
Could be, but I'm just going to use,
Like,
could be feet per second times time. Could be
Like,
miles per hour times time.
It's really tiny.
Oh, this is V sub O.
V sub O?
V sub O times time.
Okay.
Yeah, V sub O sub time. So when you throw something, it starts moving. This is how it would start moving. And if you were in outer space, standing outside a space station, and you threw something, this would be all you would need to know. It's going to keep going in the direction you throw it, and its distance will be determined by its velocity times time. You guys with me so far?
Maybe.
Excellent. Okay, so here, standing on the surface of the Earth, assuming it's roughly horizontal, here's what happens. We need to break this vector down the way we've been breaking vectors down. So when you throw something, it has a horizontal component. How do we find the horizontal leg of a right triangle drawn this way?
You find the angle. We need the angle.
We need the angle. So we need to know the angle it was thrown at. And once we know the angle and the hypotenuse, how do we find the adjacent leg? Big hint.
By using
Cosine. Thank you, Ethan. So this length here is going to be...
So it's turning into a right triangle?
Yep. Very good. It's going to be your initial velocity times time multiplied by the cosine of theta, and that will get you the horizontal leg of this triangle. The horizontal leg of this triangle is also the horizontal velocity multiplied times time of this thrown object. So that's how far it's actually going to go horizontally. With that in mind,
V0t times sine theta.
V0t times sine theta will get you, very good, Albo, will get you the vertical component of this thrown object's position. Take the velocity times the time, multiply it by the sine of theta, and that's how high this thing is going. Problem is, since we're ignoring air resistance, this is really all we have to care about vertically.
But we're also ignoring gravity in this case?
Nope, great question. Your MC just answered it. I was just going to say, what else do we have to worry about vertically, though?
You suck.
Gravity.
Well, you have to worry about a lot of things.
I do. So, this is how far it's going up, minus 1/2 gravity times time squared.
Just for that one leg?
Just for that one leg. Gravity doesn't yank us left or right when we're standing on the surface of the Earth, just down.
Wait, what did you say? It doesn't what?
Yank us left or right.
Oh, that's totally not.
Oh my god.
Okay, so,
Really?
No, actually, it wasn't that dirty, but.
all right, so vertically, we have a change in position that's determined by the initial velocity, how much time has passed, and the sine of the angle we throw it at. And then we have to take away 1/2 gravity times time squared to figure out where this thing is after we throw it. Horizontally, all we have to worry about is initial velocity times time times cosine theta. The only other thing we have to worry about is where did you start? What was your initial position?
So.
And that's x sub 0 and y sub 0. So we'll put that into the equations in a sec. May I erase this sentence? Well, I'm going to anyway. So this gives us two equations. If an object is hurled into the air and it cannot control its own position, its x position will be its starting x position plus its horizontal change, which is v initial times time,
Cosine theta?
cosine theta, and its y position at any moment
Okay.
Did you guys see
Do
that?
it! Do it!
is going to be y initial.
My power went out twice last night.
Yeah, mine too.
Probably it's the wind.
Okay? Anyway, guys, back up here, almost done.
If power goes out, do we get to leave early?
I have no idea. V initial times time, sine theta minus 1/2 gt squared. Okay, now sine of theta is just going to be a number. Cosine of theta is just going to be a number.
So wait, these equations are defined what?
These equations tell you the x and y positions, the horizontal change in position and the vertical change in position of any object that's been thrown at any angle.
It's like it tells you how far it's gone.
How far it's gone horizontally and vertically
Yeah.
separately.
Alright.
Now, the reason I mentioned dimensions are things you can see and parameters are things you can't for this lesson
Yeah.
is we're going to plug in times to figure out where an object is, but we're not going to see that. What we're going to graph is y and x. And incidentally, because of